Hi, kids. What's happening? All right, any questions on the lab and assignment from yesterday? Now, let's talk about a couple of things, okay, even if you don't have any questions. So all of these are lemming problems, which means that they all start off with no initial vertical velocity. So here's what you have to understand, is that if I roll that ball off that ramp, and it takes a path like this, okay? Or if I just drop one straight down, the only force acting on it that's going to cause an acceleration is the gravity mafia. That's it. There is nothing else, okay? So if you could view these like side by side, they would both be falling at the same vertical rate because that's the only force acting on them. We're assuming that there's nothing happening at all horizontally. So this is why in the horizontal direction, we can use range equals Vx time, okay? Because we're assuming that that velocity is remaining constant. This whole thing is just jacked up. This whole thing, that the horizontal is constant because there's no forces acting on it. Without a force, it doesn't accelerate. You do have an acceleration here because that's the direction of an imbalanced force, okay? So there's the big equations, this on the horizontal, and then you have time equals the square root of 2d over g, okay? And again, the only thing that determines how long that ball is in the air is how far it falls and your gravitational acceleration. I'm never going to give you the mass of the ball. I'm never going to tell you that it's a top flight golf ball. It doesn't make any difference, okay? It's only what's happening vertically. The other thing to find that final vertical velocity when it lands is that you're going to do that square root of 2AD. And again, the only thing that determines that vertical velocity when it lands is how far it falls and your gravitational acceleration. So you should see that as kind of the recurring thing. So on number 4 with the cliff divers at Acapulco, so this, if you can kind of get that one, you got to, I'm feeling good about life. So here's the deal. So you got to fall 41 meters, which is quite a ways to fall, okay? If you consider this ceiling is like 2.5 meters tall, okay? 41 meters is a long way. Now, outside of here, you've got rocks that extend out 12 meters. And 12 meters is roughly about the width of this room, okay? So it's a pretty good distance. So the cliff diver is going to run along, doink, and hopefully they land at some point out there. So they just can't fall straight down. They have to have a horizontal component to their velocity. So, you know how far they fall. So you can use that 2d over g. That's how long that they have to be in the air. And then you know how far from the base of the cliff they have to land. So range equals Vx time. Okay, so you know how far out they have to go. And you know how long they're in the air. And you know that range so you can find your Vx. So that answer on number 4 should be around 4 meters per second. Okay? Now that's a good thing because, you know, this is, if you will only make this mistake one time. That's your minimum velocity that you have to have. Because if it had been like 10 meters per second, don't even try it, because unless you're a world-class sprinter, you can't run that fast to get enough horizontal velocity to clear the rocks. Okay? I mean, so you got to be moving pretty quickly. You just can't stand there and go, oh, doink. Okay? You're not going to make it. You have to be running pretty quickly to clear that. Now, on number 5, here's the basic idea of number 5. So here's this dart. Okay? Now, as soon as you let go of that dart, and that's a projectile motion problem, as soon as you let go of that dart, it's going to begin to fall. Okay? And again, here's the main idea. If I just drop that dart and let it fall, or if I throw the dart, it doesn't make any difference. They're going to fall the same distance in the same amount of time. So on that one, you know your horizontal velocity, so you know how fast it's going to be moving. Those might be out. There's some, should be some over here at least. Somewhere. Yeah, there we go. Over by the water. So, you know horizontal velocity, and you're trying to figure out how far from the board was it launched. So here's the deal. You know how far it falls, okay? So in this one, you kind of have to go, oh, distance equals 1/2 AT squared, right? Plus V naught time. So there is no horizontal velocity. You know how far it falls. So you can figure out the time. Then you can do that into range equals Vx time. So on number 5, that range should make a not so good GPA. And make sure on that second part of number 1 that you just don't have, oh, it increases or decreases. Worse yet, you just say it changes. I hate the word changes. So make sure that you've either calculated that new value, or you've said, oh, it doubles, it triples, it increases by the square root of 5, whatever it is, okay? Just so, I don't care how you answer it, just make sure that get answers. So, okay. Anything else on that assignment, that lab? Any questions at all? At all? Go on. Yes?
Number 1C, is it just 0?
No. You're talking about on the back side?
Yeah.
Okay. So, here's the deal. So the whole idea of this car is that it takes off, right? And that's 112 kilometers per hour, which is 31.1 meters per second. So if that's wrong, everything else is going to be wrong, right? So in this, the assumption is that when this car falls through the air, right, that horizontal velocity remains constant. So when it lands on C, you want to find what's the horizontal velocity. That's still just 31.1 meters per second. Okay, that's the whole point, is that horizontal velocity is going to remain constant. Kara?
With the vertical velocity, when it's landing, is it always negative?
Yeah.
Okay.
I mean, yeah, technically it is if you define down as being a negative value.
Okay, so like 1D is negative 33.1, right?
No, Kara, bad. No. Okay. The horizontal, remember, what happens in the X stays in the X.
Mm-hmm.
What happens in the Y stays in the Y. Okay? So on that one, Kara, imagine this. We're just going to drop the car, and we're just going to have it fall. And we want to find the velocity that it has when it lands. So if you look at that equation, V squared equals V naught squared plus 2AD. My initial vertical velocity is 0. Okay? You know how far it falls, which in this case is going to be like that 15.8 meters.
Oh, okay. That's why it's wrong, because I plugged in my answer for 1B as my distance.
No, that's your horizontal distance, dear.
No, the range.
Yeah.
Oh,
So your answer to 1B is like 56 meters.
yeah.
Okay?
I plugged that in instead of the 15.8.
Yeah, that's why I say you have to make a sketch, and I say this again and again and again. What happens in the X stays in the X, what happens in the Y stays in the Y. So your answer to D should be around your current age. Okay? Should be around your current age.
That's exactly my current age.
Okay, all right, well, there you go. So your birthday's what, like in June?
What?
Is your birthday like in June?
July.
Okay, well, all right.
He's the only non-September birthday.
Boo,
Yeah.
get out of here.
Yeah, my birthday is September 2nd. So,
Yeah, get out of here.
Hey, my mom was born in September, it counts.
okay, there you go. By proxy, there you go. Okay. Kara, we good then?
Yes.
All right, anything else? Once, twice sold? Okay, we're done. All right, so here's the next big thing. So here's how this is going to play out. So let's say, for example, I happen to have yonder marble launcher, okay? It even says, you know, marble launcher on it. I've asked for a freshman launcher. They won't let me have one. I don't know why. So I want to use this tomorrow. But so you can adjust this angle, okay? So you can launch it pretty much exactly like horizontally, and then it would be like a lemming problem. Or you can lower it and go straight up, launch it straight up, or you can go somewhere in between. So let's say we're going to launch this thing at, say, 30 degrees, okay? Okay, so I'm going to shoot this towards Matt.
Oh, boy.
It's okay. So here's the main
I
idea.
wasn't born in September, wasn't it?
Yeah.
When this thing gets launched, right, we're going to launch this thing at 30 degrees. So when it's launched, it's going to have a vertical component to its velocity, and it's going to have a horizontal component. So when this thing goes flying out like this, there's going to be a vertical component like this, and then there's going to be a horizontal component. Okay, you ready, Matt?
Sure.
Oh, oh, hold on.
Oh,
I'll pull it back farther. Didn't make it, Matt. Oh,
I
Yeah.
hit the faucet. That's not my fault.
okay.
I feel like that was a little too hard.
I feel like we should have just.
Okay, let's try it one more time. Okay, you ready, Matt? That might go over your head. Okay, you ready?
Yeah.
Ooh,
That
good
was
catch.
Cool.
Well done.
Do it.
There we
Okay.
go.
All right, so here's how ground-to-ground problems are different than lemming problems. So with lemming problems, you had no initial vertical velocity. It was just shot out like this. With ground-to-ground problems, you have a vertical and you have a horizontal. So let's say, just make up some numbers, that
Here.
let's say it was launched at, I don't know, 16 meters per second. Okay? So let's say that was my launch velocity, 16 meters per second at 30 degrees. Now, so as this thing flies through the air, here's the first thing that you have to do on problems like this. The very first thing that you have to do is that you have to break it up into the horizontal and vertical velocities. That is the very first thing that you do. Okay, I repeat, it is the very first thing that you do. And as soon as you do that, you never speak of this 16 meters per second again. It is dead to you. Okay? Never speak of it again. That's it. It's done. Okay? So, Matt, Mr. Calculator, how are we going to find the vertical component of that velocity? Are we going to use sine, cosine, or tangent? Ms. Pfeiffer.
Oh wait, no.
I'm trying to find the side adjacent with the side opposite, and I know the hypotenuse.
So,
Beautiful. Okay, I'm going to use sine. So my Vy is going to be the velocity that it has times the sine of the angle. Okay? So in this case, I'm going to take 16 meters per second times the sine of 30 degrees. So what'd you get, Matt?
8.
8 meters per second. Okay? Now, Ms. Pfeiffer, how am I going to find Vx? cosine, right? So my Vx is going to be 16 meters per second times the cosine of 30 degrees. And what do you get there, Matt?
13.8.
13.8?
Well, 13.9.
Did you even need to do that? Because you knew both sides. You could have done 8 squared plus b squared equals 16.
I could have, but here's the problem with that, is if I don't want to do that, because if this answer is wrong, then that answer was going to be wrong. So that's why I wanted to use trig functions, because that's just going off that 16 meters per second. Okay? You could, but then you're rolling the dice. And I just assume just work off of my known values, that's all. Okay? All right. So here's what's going to happen. So when this thing launches, it has a horizontal component of 13.9 meters per second. Now, Shivani, as it flies through the air, what's going to happen to this horizontal velocity? Is it going to increase, decrease, or stay the same?
Stay the same.
Stay the same. It's still the same idea. So, as it flies through the air, that Vx is going to stay the exact same, even when it lands. Okay? Even when it's up here at the top. Okay? When it's at the top of its flight, it's still only going to have a horizontal velocity of 13.9 meters per second. So if you look at that trajectory when that marble was shot to Matt, okay, at the very top of the flight, it's going to change direction vertically, but it's still going to have a horizontal velocity to it because it's still going to be moving, okay? So when it hits the top of the flight, it has no vertical velocity, but it still has a horizontal velocity, okay? Now, Kara, it's going to start with an initial vertical velocity of 8 meters per second. So as it flies through the air, what's going to happen to that vertical velocity as it goes up?
It's going to decrease.
It's going to decrease, right? Because gravity is pulling it down. Oh, okay, right? So that vertical velocity is going to get smaller and smaller and smaller. When will that vertical velocity go to 0?
It's at its highest point.
Beautiful, when it's at its highest point. Okay? Now, on the way down, Kara, what's going to happen to the vertical velocity?
It'll be
Yes?
negative.
And getting bigger or smaller?
Well, technically, it's getting bigger.
Yeah, and the negative sign just tells us which direction that it's going. Okay? So then you're going to have some negative velocity. So when it lands, assuming, and this is a huge if, assuming that it lands back at that same point, it's going to land at negative 8 meters per second. Okay? So, and at any given point in between, just like you all did in the lab, you can find that horizontal and vertical component resultant, which is going to be the actual speed. So as it flies through the air, that flattens out because my vertical velocity is getting smaller. Then it gets bigger on the way down. Now, right now I want you to all pretend that this number, none of this exists. Okay? It's gone. It's out. Okay? Don't even worry about it. Okay? So I'm going to throw a ball up in the air at 8 meters per second. Okay? Like that. I'm going to give it a toss. 8 meters per second. Don't worry about projectile motion. Pretend that you're getting ready for the acceleration test. I want to find the time up. I want to find the time down. I want to find my maximum height. Okay? I want to find all of those things. And then I want to figure out how high it is at a half a second. Okay? So, we're going to toss this ball up in the air with an 8 meter per second velocity. I want to find the time up, the time down, my maximum height, and how high it is at a half a second of the flight. Now, Matt, before we do any calculations, what's my velocity time graph going to look like?
start at pi, and then just be a straight downward sloping line.
Like such?
E.
Cool? Okay. Shivani, what's the slope of that line going to be?
-9.80 meters per second.
Beautiful. Okay, got the slope of the line. Now, Karen, I want you to think very carefully before you answer this question. Is my time up, okay, the time up, is that going to be bigger or smaller than 1 second?
Smaller.
Yes. Why?
I don't know. You threw it up and I was like, that's not 1 second.
You're assuming I threw it at 8 meters per second, though. Karen, let's think this through.
8 meters per second. I get it. I get it. And that wasn't 8 meters.
No,
Oh. Oh my god.
no. Karen. What this slope means that for every second that goes by, my velocity changes 9.8, right? So if I started at exactly 9.8 meters per second,
It'd be 1 second.
it would take exactly 1 second,
Yeah.
right? Since my velocity is less than 8 meters per second, guess what?
It'll take less than a second.
It's going to take less than a second for it to fall.
Yeah.
Okay?
I'm just a bit slow. It's early.
I know. That's why we walked you through this. Okay? That's why we walked you through this. Okay? So, I know my time up is going to be less than a second because my initial velocity is less than 9.8 meters per second. Okay? So don't lose track of what we've already learned. Okay? So, how can I find my time up, Miss Pfeiffer?
Witchcraft.
Witchcraft. Okay, that's a good. Don't discount that as a good answer. So on the way up, Miss Pfeiffer, when it reaches this maximum height, what's the final velocity going to be? You know your initial velocity. You know your acceleration. Okay. So what relates initial velocity, final velocity, acceleration, and time? Beautiful. So my time up is going to be V minus V naught over G. So Matt, take 0 minus 8 meters per second and divide that by negative 9.8 meters per second squared.
0.816.
What'd you get? 0.81?
6.
Call it 0.82 seconds. Okay? All right, 0.82 seconds. So Kara was right? Because it's going to take less than a second to go up because of the fact that my initial velocity was less than 9.8 meters per second. Okay? Cool with this. So I throw this ball up, 0.82 seconds later it's at its maximum height. So Shivani, then what's my time down going to be, assuming that it returns back to the same point?
0.82 seconds.
Beautiful. That's also going to be 0.82 seconds. Okay? It's kind of cool, right? So if I were to look at my velocity time graph, there's 0.82 seconds. And then that's going to be 1.64 seconds for the entire thing. Okay? Got that. Now, if we assume that this number is right, how could I use this graph to find the maximum height?
The triangle stuff.
Yeah, I could just find the area of this triangle because the area of that triangle gives me displacement, right? Which would be the distance that it's going to go up. So one option is that I could take 8 meters per second times 0.82 seconds and take half of that and get the area of that triangle, right? So we'll kind of go old school review. So if you do that, Matt, what do you get?
3.27.
3 point what?
27.
Okay? Now, that would be higher than the ceiling because the ceiling's only like 2.5. So I couldn't do this in this room because I'd hit the ceiling and that would be bad, okay? Now, what's the disadvantage of finding my max height this way?
You're using calculated values?
Yeah, if this 0.82 seconds is wrong, the next part's going to be wrong. So how can I find my maximum height without using that time?
That equation.
I could use that equation. Oh, okay. So I could go v squared equals v naught squared plus 2ad, right? Okay. So I could go v squared minus v naught squared over 2a, which in this case is going to be 0 minus 8 meters per second squared divided by 2 times g. And I'm guessing, Matt, you're going to get about the same answer. So 64 divided by 19.6.
Yep.
Yep, you get about 3.27 meters, okay? Because I can't have one set of equations producing one answer and another set of equations producing another answer. Okay, so now I have my maximum height. Like I said, which is going to be higher than this ceiling. All right. Now, we got that. We got the maximum height done. So the only thing we have left to do is figure out how high it is at 0.5 seconds. Now, there's only one way you can do this, okay? The only way you can do that is to use that function equation, distance equals 1/2 at squared plus v naught time. That is the only way that you can solve this problem, okay? There is no other way you can. So this is like that mortar problem, you know, when I said, hey, how high is the mortar when it explodes, okay? It's a function equation. That's the only thing you can do. Now, here's what you have to be careful of. You're going to have 1/2. You have to use negative 9.8 meters per second squared. Now, I tell you the specific time at 0.5 seconds. Don't take half the time. Don't take that and go, oh, that's going to be 0.25, okay? That's only if you have like the entire flight time and you're trying to figure out how high it is at its maximum height, okay? Don't. Just plug in the 0.5 seconds. So that's going to be 0.5 seconds squared. Now, in this situation, and again, what happens in the vertical stays in the vertical. What happens in the x stays in the x. So in this problem, here's what you have to be careful of. Like if this had been the actual problem, don't plug in the 16 meters per second that it's launched at, okay? Don't use the 16. The only thing you're going to use is that vertical velocity. That's why I said that 16 meters per second, you use it to find the x and y components, and then it's dead to you, okay? Don't use it again. So anytime you're going to be using this vertical acceleration of negative 9.8 meters per second squared, make sure that you're on this initial velocity here, that you're only using the vertical component of the velocity, okay? You only use the vertical component, which in this case is going to be 8 meters per second times 1/2 a second. Now, what does my answer have to be less than?
3.27.
Beautiful. It has to be less than 3.27 because 3.27 is my maximum height, okay? Now, is the ball on its way up or is it on its way down, Kara?
Up,
Why?
because it reaches its highest point at 0.8.
Beautiful. Fantastic. So we're here at about 0.5, so my velocity is still positive, ball's still on its way up, okay? So, Matt, run the numbers. Take negative 4.9 times 0.5 squared and add that to 4. 2.78 meters. Okay, so Sivani was right. It's going to be less than that maximum height. This would be about the height of my ceiling at that point. Okay, so here's the cool thing about this, is that allows you to calculate a height at any point in time. Okay, doesn't make any difference. There you go. Okay, I'm done. Okay, so let me kind of lay out the scenario on these problems, right? So on number one, here's the scenario. You have someone pitching, okay? And they're going to throw the ball as a lemming problem, okay? It's a lemming problem. This isn't a ground-to-ground problem, it's a lemming problem. So it would be like me taking this ball and I'm going to throw it to Matt, and I'm going to throw it exactly horizontally, okay? So here's the catcher, okay, right? Ball's going to come in here like this. So in one situation, you throw the ball quickly. The other scenario, you throw it a little bit slower. Now, here's the deal. This isn't about which ball goes farther, okay? They're both going to be caught by the catcher, okay? So the range is going to be the same, okay? They're both going to travel to the catcher. They're both going to get caught. The question is that why is the ball that's thrown slower, why is it going to end up lower in the strike zone, whereas the ball that's thrown faster is going to end up higher in the strike zone, okay? So think of this in terms of time, okay? Think of it in terms of how long gravity has to act on the ball as it falls, okay? Now, when you get to number two, I emphasize this. So you have a Teflon puck, okay, that's moving at 5 meters per second. And I've given you the mass, and it's moving on a frictionless surface, okay? So listen to me, listen to me, listen to me. The puck is already moving. You don't have to push it. It's already been pushed, okay? It's already moving. Don't push it, okay? It's moving on a frictionless surface at 5 meters per second. So I've got the hockey puck drawn at a couple of places, like this, okay? And I tell you, right here, this hasn't hit the ground. But it's like literally, you can just slide a piece of paper underneath it, okay? So it's that absolute split second right before it hits the ground, okay? It's real, real close, but it hasn't hit the ground yet. So the first thing that you want to do is that you want to draw all of the forces acting on the hockey puck. This is to scale, okay? You're going to use a ruler. So you have the mass, it's 0.1 kilograms. 0.1 times 9.8, you get 0.98 newtons. So make it simple. You could like let a centimeter equal a newton, okay? Something like that. I don't care how you set up your scale, just set up a scale, okay? So you're going to draw the forces acting on it here, 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 okay? That's what you've got. Now, on part B, you're going to draw the acceleration vectors. So your acceleration vectors are going to be driven by your force vectors. So if all of your forces add up to equal to 0, you don't have an acceleration. If you have an imbalanced force, now you have an acceleration. So to figure out what happens with your acceleration, you have to look at your forces, okay? And again, set up a scale. Maybe 1 centimeter equals 10 meters per second squared, or something like that. Okay? Again, you're going to draw that with a ruler, and you're going to show me what that scale is. Okay? Now, on the third diagram, that's going to be your velocity vectors. So, and again, to figure out if your velocity vectors are changing, look at your acceleration vectors. If you're not accelerating, your velocity vectors aren't changing. If you are accelerating, then your velocity vectors are changing, okay? So your forces drive your acceleration. Your accelerations drive your velocity vectors, okay? And again, it's traveling at 5 meters per second. So I would let maybe 1 centimeter equal 5 meters per second, okay? There you go. So you're going to have 3 different scales. A scale for your forces, a scale for your accelerations, and a scale for your velocities. Make sure that you clearly draw that out and lay that out so I know exactly what's happening. All right, on the back side. So questions 3 and 4 relate to the hockey puck problem from before. Okay, that's what that's dealing with. Now, when you get to question number 5, so you're going to hit a golf ball at 32 meters per second at an angle of 30 degrees. So what's the first thing that you're going to do with that vector?
Split it up.
Yeah, you're going to find the horizontal and vertical components of that velocity. Okay, there you go. Now, you eventually want to find the range. So if you go back up to this problem, now that we know that total time, like in this problem, if we wanted to figure out how far that ball was going to go, okay, now that we know our Vx, we could take that horizontal velocity of 13.9 meters per second, because we know that's that horizontal velocity. We know how long it's in the air, right? So we could take that horizontal velocity, multiply it by our total flight time. Hey, that's how far it's going to go. So that's the easiest way to, that's what you're going to do on 5 and 6. So you're launching this thing at 32 meters per second. Find the x and y components. And then never speak of that 32 meters per second again. Okay? It is dead to you. Don't use it again. You're only going to use your x and y components. Okay? Now, the only thing that changes on number 6 is that you're still going to launch it at 32 meters per second. But now you're going to launch it at a much steeper angle. So now you're going to hit it at like at 60 degrees. But you're still going to leave at 32 meters per second. Again, the first thing that you're going to do is find the x and y components of that velocity. Okay? All right, now, when you get to number 8, this is the most complicated problem that you've got. So you're on top of a cliff 20 meters high. You're going to launch the golf ball at 40 meters per second at an angle of 60 degrees, and it's going to go like this. Okay? Now, this is like, if you remember back to your acceleration test, where y'all did a problem where you threw the ball up off the top of the building and it fell all the way down to the ground. Okay? It's the exact same type of problem this is. The only difference is that you have an x and y component to that velocity. So let me kind of give you a hint. Find your Vx, find your Vy. Okay? Once you get that Vy, then just sit here and go, oh, okay, how high is it going to go? Oh, I can use that equation. Then you're going to know how high it is. You're going to figure out, you can find the time up because you know your initial vertical velocity. Then at that point, it's going to start to fall. Then it becomes like a lemming problem. Because if you think about it, once it starts to fall, you model it like a lemming problem. Oh, I know how far it's going to fall. I can find out how long it takes for it to fall. I can find the final vertical velocity when it lands. So your ultimate goal is D when it asks for the speed. So when this thing lands, it's going to have a Vx and it's going to have a Vy. Okay? So your speed is going to be the resultant of those two. Now, think this through. It's going to launch at 40 meters per second, but it's going to fall all the way down here. So when it lands, is this speed here going to be bigger or smaller than 40 meters per second? Bigger. Because it's going to have, when it lands, it's going to have a bigger vertical component when it lands than it did when it was launched. So this answer here for your speed has to be bigger than 40 meters per second. Now, when you get to E, you're at the top of the flight, okay? You're at the top of the flight. You're at the top, okay? And it asks, what's the angle between the velocity vector and the acceleration vector? So imagine that you're at the very pinnacle of this flight. Think this through. What velocity is it going to have? In which direction is that going to act? what's the direction, if it's accelerating, and it is, what's the direction of that acceleration? So you're at the very pinnacle of that flight. So think this through. What velocity does it have? And what acceleration does it have? Okay? And then look at that in terms of that angle. Okay. I'm done. I don't feel well. You're on your own. So, let's make magic.